People are started to join one by one, so we can wait. And maybe we will wait like a minute, 9:03, and we start right at 9:03.
Sure,
Yeah.
and it's like 40, 45 minutes?
Yeah, I mean, up to you. I mean, yeah, 40, 45 minutes is good.
Yeah, and Navid, I can take care of admitting people after the seminar starts, so that you know.
Oh, thank you.
Yeah, because I'm sure people will keep joining. You know.
Join. Yeah. Thank you. Yeah. Okay, so maybe we can start, just given the time line. And hello, everyone. And again, if you're just joining, thank you for joining to Advanced Composite Center Seminar Series. We are very happy to host Paul Davidson from University of Texas, Arlington. Paul is a good friend and also very savvy scientist and engineer.
Thanks.
Paul was part of UW family for 2 years. I just realized it was 3 years. I thought it was much longer, but for 2 years. And as it is with good people, they leave to other places. So Paul left us, and now he's an assistant professor at the University of Texas, Arlington. And so just I'll give a brief overview of Paul's background and bio, and then I'll let Paul to go through his slides, because I'm sure everyone is eager to look at his research. So Paul is at the Mechanical and Aerospace Engineering at the University of Texas at Arlington. He has supports from industry and DoD, and his area of research on material design and computational methods for manufacturing, durability, and damage tolerance of composites. And we are very eager to listen to his work related to automated fiber placements of composites. Thanks again, Paul, for joining us. And please take the slides and start your presentation.
Thanks, Naveed. It's good to look at see some familiar faces from my time at UW. And I fondly remember my time at UW, but I also don't miss the gloomy, rainy part of it. But yeah, it's an amazing university. It's an amazing place, amazing set of people. So I'm glad to be giving a seminar on what I'm doing. In fact, most of my AFP work started at UW. So I worked closely with Electro-Impact at that point. We did some very cool experimental work as well as manufacturing work. And since then, I've started working on AFP exclusively. And today I'll be talking about how we are trying to create digital process twins. And I'll focus mostly on the heat transfer problem. So as Naveed said, I'm at UT Arlington. And my lab at Arlington is called the Laboratory for Advanced Materials Manufacturing and Analysis. I wanted the acronym that supports a mascot. That's just how it came about. All right, so to introduce my lab, we have 4 PhD students, 1 undergraduate student, and 2 alumni of our lab. So most of the work I'll be showing you here is what my students are doing, and also collaborations with other professors. So goals of the lab itself are threefold. And as everyone likes to look at Venn diagrams, I'll show my Venn diagram. So the goals are to work on the materials, manufacturing, and analysis, and the intersection of that. So LAMMA, we are aiming to work in all these 3 areas. And whatever I've shown on the sides are the active kind of work we are trying to do. Research priorities, we work everything from fundamental work, fundamental sciences to applied. And whatever I have in green are some of the active work we are doing right now. Some of the work in multifunctional materials is just starting, so that will be something we are really interested in. But our overall goal is to introduce digital process twins and use some sort of AI ML to use reduced order modeling. So next, what I'll go through is some of select projects which we are doing in the lab, just to give you a flavor. Sandesh is working on looking at stiffened structures with AFP. So the idea is to be able to generate stiffened structures with AFP, but how can we replicate something similar to what we see in nature? So Sandesh is working on semi-analytical methods for buckling load optimization, where we vary thickness as well as fiber angles. And then a natural segue to that is to look at isotropic plates. And we are also looking at isotropic plates because in addition to our AFP, we have an extrusion head, which can lay down just polymer matrix composites, right, without any reinforcement, isotropic case. So that is what Sandesh is doing. We are also doing damage risk assessment for due to impact, where we are using machine learning models to be able to go from raw inspection data to some sort of strength prediction or the risk of compression after impact. Of course, as you know, with machine learning, we require a lot of data. So, and experimental data is hard to come by, as Naveed knows well. So we are using a sort of a data fusion technique where we use analytical models combined with impact simulations and for CAI simulations to be able to generate the missing sort of data. So we develop a lot of work in computational models for impact and how we can introduce new techniques to be very accurate to what we find in the physical impact. So here, Oscar, Don, and Juan are working on this. This is a project supported by AFRL. In addition to that, AFRL is also supporting a work by another student, Mark, where we are looking at mechanics of deformable metamaterial sheets. So the idea is to understand how the deformation of metamaterial sheets work and to be able to homogenize it using novel techniques like micropolar or just typical homogenization using finite elements. Then there are other projects where we work with Northrop Grumman to look at Z-pinned reinforcement and how we can characterize the cohesive behavior for the interface with the Z-pins. Then I'm working with Dr. Amir, where we are looking at changing or tailoring material properties for 3D printed metal parts, where we can then use it to do novel ways of deflecting cracks or making sure the cracks go the way you want it to go. So there's a video which shows that we can actually change the crack path. If you have seen typical metal testing, you get the necking and failure. Here we can actually make the crack go at a very defined biased angles. I don't know if you can see that, but yeah. Then of course we have fun projects where we look at doing some, off the topic work where we are doing soft actuators to actually actuate soft bodies. So this is like a twisted coil actuators where you can actuate soft bodies by just providing some sort of electrical input. And also thermal input. So we can do, folding of structures of soft bodies by just providing some heat input to it. So, but all of us devote quite a bit of time in automated fiber placement technologies. And we have at LAMMA developed our own system in collaboration with AdPath and Helios or Hum3. So the system is slightly different what you would see from typical research systems. It's a two-toe system. And the idea is that you can have different toes and use that for laying down hybrid composites. And we use Hum3 Xenon arc flash lamp heating system in lieu of, instead of laser-based system to do thermoplastic layup and consolidation. This system, since we integrated it ourselves, everything was kind of done in-house. It's extremely customizable, so we can introduce our own, ways of doing measurements, introduce our own ways of doing path planning, as well as do any kind of stuff we want. And I'll show you some examples of that. But the basic system of the AFP is this. And here is a video which shows how the system looks like in actual work. And this is for a thermoplastic laydown. And you can see it essentially is a very bright light, which imparts near infrared radiation to heat up the material system itself. But this is our initial trial, but you can see within the initial trial itself, though not completely consolidating or bonding to the surface. And then if you think about it, that is essentially a very complicated problem to solve. And that problem is what we call the heat transfer problem. So of late, we have been working on exclusively devoting our time on understanding what the heat transfer looks like for an AFP system and specifically for Xenon flash lamp-based system. This is the work we are doing with the multi-scale thermophysics lab at UTA, which is run by Dr. Ankur Jain. So just taking a step back and looking at AFP laydown for carbon fiber in thermoplastics, I've shown you, I just want to go through kind of the steps we go through or what the machine goes through. So if you think about simplistically, you have a roller and you have a tape under tension, and the roller compacts as the tape is moving while the tape and the substrate is heated using a heat flux. So there are three essential steps to AFP in situ consolidation. One is heating. So you have the incoming tape and the substrate tape where you impart heat flux. And during consolidation, the top and the bottom tape come together. That's the incoming and the substrate, wherein you have intimate contact, cross-interface diffusion. And then when you cool down, you essentially heal the system. And then you're supposed to have a homogenized interface which has through cross-interface crystallization, as well as some amount of crystallization within the tape itself. But if you think about the overall scheme of what a single material point in the whole panel or the whole structure looks like or undergoes, it is a multi-cycle step. So initially you go through pass one, which is the initial pass when you lay down the tape. But as more material is added from tape to tape, and as the part is being built up, the same material point will go through multiple cycles of heating and cooling. Not just heating and cooling, but also the pressure cycles. So what we want to understand is how the material behaves as it goes through each of these heating and cooling cycles. How does it influence the crystallization and so on? But if you think about the overall boundary conditions or the loading on the tape itself, so let's look at 4 time points. And if you imagine the material going through each of these time points, T0 to T4, I'm trying to depict what happens to the material. So as the tape is at time 1, it is only under tension, right? There is no other boundary condition being applied. As it goes through, you are heating the tape at T1 only on one side. So you apply some sort of flux, and then it attaches itself to the roller. It goes through lower roller, which imparts one-sided compression, and then you have a bending. So the tension in the tape increases, and also you introduce shear. Then once it goes to T3, where you have the substrate, it comes under contact with the substrate. Now the tape is under compression, tension, and it is hot. That means it is trying to go through thermal cycle. And finally, when it goes through cooling, you have, the tape is recrystallizing or crystallizing, and then you have, internal residual stresses develop and so on. And then there is complication with heat transfer. At the macro scale, you have radiation on the surface, and some of the radiation is reflected back. Then there is conduction within the tape and between the tape and the roller or the mold surface. And then as it's cooling, you have convection, and you have all of this happening through some sort of velocity of the air around the tape itself. So this itself is a complicated process, and this is at macro scale. But if you think about what happens at the micro scale, the surface of the tape is very uneven due to the very nature of it being a heterogeneous structure. And because of this, you have an incident. If you have an incident laser light, you have non-specular reflection, specular reflection, some amount of energy is absorbed, and some is transmitted through. And then what is even more interesting in thermoplastics is that for the given incident energy due to laser, specifically here, all these studies are done on laser, the material, that is the thermoplastic material itself, PEG or whatever thermoplastic you use, is essentially transparent to the incident radiation. And that is because the absorption, radiation absorption of the material is at a much higher wavelength than what you would have for a laser. So material like PEG will have an absorption at around 3000 nanometers, whereas the incident radiation, typical laser radiation, is around 980 nanometers. So essentially, the laser goes through the matrix without even heating it. The heating happens because the laser incident on the fibers, and the fibers heat up, and then you have a conduction between the fiber and the matrix to heat up the matrix itself. And so if you look at the penetration depth of the laser itself, you have a non-linear distribution from the surface to the bottom. And recently, there was a very interesting result by Stotty, where they did a simulation using ray tracing, and they show that it's only the initial few layers of the fibers which actually get heated up. Rest of the fibers do not actually even see the incident radiation. And because of this heating of the fibers, we have heating of the matrix itself. So it is never a direct heating of the matrix itself. So there is a two-scale problem. At the macro scale, you want to look at how the tape behaves, but at the micro scale, you want to look at how the constituent behaves. And it's the interaction between the two that ensures the right temperature is achieved when you're laying down the tape itself. So in our case, it's slightly more complicated, and I'll kind of talk about why. But what we wanted to do was go through the whole understanding of the process. And the reason is because as I mentioned, it's a very complicated process. So if you're laying down a whole structure, you need to know a priori what the structure needs at a given point as is being laid down in terms of heat, in terms of pressure. And if the structure is complicated, that means it has a lot of curvatures, then the velocities will change as you're laying down of the AFP. So what should be the heat transfer or the heating mechanism or amount of incident radiation required to achieve the temperature you want? So to do all of that on the fly, as you're designing the part, you really need to have a digital twin, right? Because otherwise, if you're trying to do it empirically, it is an unsustainable problem. You cannot do all of this empirically. So we need to have a digital twin of the process itself. So what we did was we started off by trying to understand what we have. That means how is the arc flash lamp behaving in our problem, in our AFP system. So the first question we ask is, what is the incident radiation? And to do that, let me first explain what the heating system in our setup looks like. So in our system, we have a lamp head. Inside the lamp head, we have an Xenon arc flash lamp, which basically develops high frequency pulses of plasma, and the plasma radiates at different incident wavelengths or the radiation wavelengths. And then all of that radiation is focused using a quartz guide. So if one were to think about what are the parameters that can go into the processing of it, it depends on the location of the quartz with respect to the toes and the substrate. So that means there is geometrical parameter, and of course, what the power of the lamp is. And the power of the lamp is controlled by the pulse frequency, pulse width, and the voltage. So essentially, there are two process control parameters for our system. So our question was, how can we use these control parameters to get the temperature what we need at the nip point? So that temperature is the temperature of the toe as well as temperature at the substrate. And that is important for us because unlike laser systems where you have a very narrow range of infrared heating, this is the spectrum of the flash lamp itself. So you can see we have some amount of ultraviolet, very high, the full spectrum of visible range, and a very broad spectrum of the near infrared. So unlike laser, where you typically operate at 980 or 950 nanometer scale, we have everything from 700 to 1200, right? So we needed to know how this broadband spectrum influences the heating in our tape material system. Not only that, depending on your pulse parameters, you can get very different irradiation levels. So to do that, we first started off by characterizing our heating system, and that is my talk today, how we characterize it, the novel ways we used to characterize the lamp itself. So we first develop a gantry style or a mini gantry style system where we look at the flash lamp using a very cool sensor, which is the flux sensor. It's a thermopile. And what we can do with the gantry system is move the thermopile or the flux sensor around the flash lamp head or the quartz at different locations and characterize the whole envelope of the radiation coming out of the quartz block. So to do that, we kind of created a grid, and this is all at different lengths. So it is 6, 12, and 18 millimeters off from the facets. And then we looked at three planes of measurements. That is the mid, the positive edge, and the negative edge. And then we essentially ran a DOE to look at how different power values and the different distances influences our readings or the parameters of incident radiation. And then if you look at the measurements which we get, you can see that for a given power, so we looked at three powers, 1,240 watts to 4,000 and 7,000 watts. For any given reading, the value of incident radiation is not a fixed value. And we are pulsing the light at a given frequency. And because of that, you get these very high oscillations in your incident radiation itself. But on an average, the values are fairly smooth, right? So depending on how far you are from the quartz facet, you can get different values of incident radiation. And then we average out the incident radiation over a time period of about 5 seconds to get a reasonably good result. And then what we can do is interrogate that profile and see how the incident radiation changes with respect to, say, linear distance and at different locations of the quartz itself. So here I'm showing you, how the incident radiation changes. And as one would expect, as the linear distance from the quartz itself increases, the value decreases. However, depending on where you're located within the quartz block, your value can decrease at different rates. So this is at the edge where the rate of change or rate of decrease is fairly linear. But as you go through the midplane, the rate of change is nonlinear. And with that, now what we can do is generate a whole envelope of flux around the quartz block itself. And we do that using radial basis function. So take the measurement, what we have made, and you fit the whole thing using radial basis function and create a 3D irradiance profile. And so in the white region in the middle is the quartz block, and the colored region is essentially the flux profile which you get. This is all taken at midplane, but you can imagine that we can do it for any plane within the quartz block. So this is the profile of radiation which we get for 7,000 watts, 4,000, and 1,200 watts. As you can see, the profile itself is similar as you go from, as you change the wattage. But within 1 wattage, it is extremely nonlinear. And a tape is essentially, or material point is essentially passing through this nonlinear flux profile. So it is not the same incident radiation, but the radiation changes as you move, the tape moves through this flux profile, right? So that becomes a very complicated problem because now the material does not see the same flux, and the time history of the flux now matters, right? Okay, so all right, so then what we did is to understand that we said, okay, if we were to do measurements for everything using experiments, it is intractable. I mean, there'll be so many experiments to do. So we said, let's first see how these flux profile influence the temperature on the material by first looking at a static test. That means we take the quartz block and then we put a region of tape or a sort of plane of tape at different locations around the quartz block and measure the temperature. So we did it for 3 locations, which is facet 2, facet 4, and then facet 3. So facet 2, by facet 2, I mean that you'd keep the plate parallel to facet 2, then parallel to facet 4, and then parallel to the facet 3, which is right on the top. So if you look at the incident radiation profile, which we can estimate now because of the fact that we have now an envelope, we can put the plate at different locations through and then interrogate what would be the flux profile on the plate itself. And this is what the flux profile looks like. When I first saw it, it reminded me of a Rorschach test, but this is quite interesting. So you can see, depending on the facet, and depending on the location of the plate itself, you get a very nonlinear distribution of the irradiance. So the question was, can we replicate this and measure the temperature both numerically and experimentally? So we first measured the material properties of the tape itself. We got the density from the data sheet. We did thermal conductivity test using laser flash analyzer. We did specific heat capacity using DSC. There were some outliers which we ignored. Then the main challenge is getting the convective heat transfer coefficient. And as you know from basic thermal engineering classes which you have taken, this heat transfer coefficient is extremely dependent on how the air moves around the tape itself. So for example, if one were to look at the convective heat transfer coefficient for this versus this, that means parallel to facet 2 versus parallel to facet 3, that can change because of the way air is heated around the tape itself during each of these experiments. So we did do calibration for one of the experiments and then started using that to see how best we can replicate the other experiments. So we ran a heat transfer simulation model, which is a fairly straightforward model using transient heat analysis in ANSYS. So essentially we take the plate, we replicate the plate, and then we apply all the boundary conditions. And specifically the boundary conditions on the flux we take from our radial basis function interpolation, right? And then we ran 2 analyses two-step analysis. One is heating of 2 seconds or 0.2 seconds, then a cooling of about 30 seconds. And as with any finite element modeling, you need to do mesh and time step convergence study. We did that, and it converges very quickly. And our element sizes are much higher, and our time steps are much smaller than what is required. And then we did sensitivity study. So what was interesting is that in the sensitivity study, we can see that our dependence on H, which is the convective heat transfer, during heating is minimal. So it doesn't matter what convective heat transfer you choose. Most of the heating is dominated by the radiation and the radiation problem. On the cooling side, though, it is extremely dependent on the convective heat transfer. Now, this becomes important because if you think about the AFP process, you are laying down a tape as it's moving, right? And then as you're passing the tape for the second pass or the third pass, the airflow around the surface of the material itself changes. That means your convective heat transfer coefficient changes. That means your cooling rates can change based on the motion or the flow around the surface post laying down. Yeah. So it is not simple as saying that there's one natural convection heat transfer coefficient we can use. We have to actually be able to predict what the H value would be to be able to get the correct cooling rate and then consequently the correct crystallization behavior. Anyway, so that was a very interesting learning from this. And then we did calibration studies and see how sensitive the calibration was. And you can see that even if you increase or decrease by 10%, the temperature readings which we get was fairly close to the experiment. And it is extremely insensitive to any noise in our simulation. So with that confidence, we then did the full temperature evolution for facet 4. Top is the experiment, and bottom is the simulation. And you can see that our temperatures matches up quite well. Not only the temperatures, even the distribution or the rate, the area of coverage of the temperature matches up quite well. This is further verified by looking at comparing experiment to simulation for different facets. So this is for facet 2. This is for facet 3, which had a very complicated radiance profile. Both the heating and the cooling matches up quite well. And these are for facets 4. So here the heating matches up very well with the experiment and so on. And then we also can interrogate what happens at different locations within the panel itself. So here we took a horizontal line and looked at how the temperature changes. Here we took a vertical line and looked at how the temperature changes. So we have now confidence that our experiment and simulation matches up quite well. Of course, there's room for improvement. For example, we don't have exact profile as we move away from the hotspot. And that can be attributed to the fact that it might not have the same heat transfer coefficient across the panel, right? So there are certain things we still need to calibrate or we still need to work around and see how we can improve the results, but overall, the results match up quite well. So now the question is, what do we do with all this? Now we can actually start looking at the process thermal property relationship, which ultimately goes into our digital twin behavior, digital twin itself. So now that we have full understanding of the heat transfer at the macro scale, we need to understand how the motion of the quartz as you're laying down have an impact on the nip point temperature and indeed the temperature profile on the toe and the substrate. So to do that, we looked at these parameters. The first one we already talked about, the quartz power. We looked at how the quartz angle, the linear distance of the quartz with respect to the toe and the substrate, the compaction of the roller and the toe layout speed influences the irradiance profile as we move through it. So This is the baseline study where we look at how if the toe is moving at a given velocity and a profile of 7,000 watts, what would be the temperature on the incoming toe and the substrate. So to read this is that at zero distance is the nip point, which is this point right there, if you can see my cursor. And then if you're looking at the blue curve, that is the incoming toe. So from there, if you go up the toe, that is the irradiance profile you get. And then if you look at the substrate, that is from the nip point going this way, right? So with this, you can see that the maximum irradiance which you get is not at the nip point. It is, in fact, quite far away from the nip point, and that is by design. And that is because there is a thermal mass as the toe is passing through the flux field. The thermal mass is such that it allows for conduction within the toe to happen and then heat up the material, that is the thermoplastic. And that time is, or the distance is required for that to happen, right? So as we know, it is the fibers which heat up and then heat up the matrix itself. But for joining of two surfaces, we need the matrix to melt to be able to join the two surfaces. So then we can now look at how, the distances, like linear positioning of the quartz, can change. So if you look at the linear positioning of the quartz, the heating is the same, but with increasing distance, you get less irradiance. The intensity of the irradiance changes, but the location is the same. Now, if you change the angle of the quartz, you can change the distribution of the energy as it's coming on the tape as well as the substrate. And then if you combine all the influences, we can look at how the geometric distribution changes your intensity of the flux itself. So this is the nip point radiance. If you know the nip point radiance, then we can calculate what the intensity of flux was at different locations within the toe and the tape. So as you can see, there is a non-linear, or rather a linear kind of sort of behavior. As you move away, you have a reduction in irradiance. As you change the angle to be more shallower, you get reduction and vice versa. Then we can also look at how compaction influences it. So if you compact it more, your nip point shifts towards the quartz block, and that increases the irradiance, but it also reduces the time it has to conduct within the tape to get you better adhesion, right? Then we can also interrogate how the velocities influence your irradiance profile. Okay, so with that, we have a fairly good idea of how the whole irradiance works, and now we have a numerical model which can calculate how that irradiance influences the heat profile on the tape itself. So that is essentially what we have done so far, and what I would like to show. But in addition to that, what we are also doing is improving our testing approach. So previously we showed you we use a gantry style, mini gantry style manual control. Now the beauty of our system of AFP is that since we are integrated it, we can also dismantle it. So we dismantle the AFP, put our sensor there, and then we can do, instead of 187 points, more than 200 data points to really get a good profile on the flux itself. Then we are also doing moving platform tests. That means we take the material and pass it through the flux profile at different velocities, and then characterize the material itself for both crystallinity as well as distribution of crystallinity through the thickness of the tape, and see how the flux profile and the velocities influence that. And finally, we also doing modeling, a lot of modeling effort. We start with ray tracing to look at exactly how the rays come out, and this decides your distribution in flux. And then we are also doing multi-scale modeling to look at the evolution of crystallinity, both in terms of transcrystallization around around the fiber, as well as the spherulite development on the matrix itself. And that's basically the work we are doing, and I'm happy to take any questions. I think I'm right on time.
Thank you. Thank you very much, Paul, for a very interesting presentation. I myself have a lot of questions, but I will let the audience to ask questions. And if we can't ask the questions here, I'm sure we can find time later to connect with you. But maybe I ask the audience, if you have a question, please raise your hand and ask the questions.
So Naveed, I might have to run soon, but can I ask my question first?
Yes, go ahead, Professor.
Okay. So Paul, like super interesting talk. I'm just curious, like does the type of fiber change the the heating behavior of the material, and is that like how big of a parameter is that, if any?
Right. So, well, if you're talking about glass versus carbon versus boron, it does, right? It all depends on what is the absorptivity of the fiber itself. So carbon fiber, fortunately, has a very broad absorptivity. So if you can take anywhere from near infrared to mid infrared range of flux. So carbon fiber that way is better, but if you look at glass fiber, it does not absorb near infrared that well. And I don't know about boron, so I can't comment on that. So it does matter. The type of material used to create the fiber makes a difference.
So even if, let's say, you have like something like AS4 versus T1000, which is like so different, even at the structure scale, you would not see differences with laser?
No, I don't think so, because the absorption is still carbon-based, right? So absorption characteristics will not change for the fiber itself. Not that much. I'm sure there's some changes, but not as much.
I see. I see. Super interesting. Thanks.
Thank you. Other questions from the audience? Or maybe I'll jump in because I have a list of questions.
Sure.
So I think one thing first of all, appreciate all the complexities that you explained that happens during heating, which is a lot. The list is endless of the parameters that might influence the heating and cooling, as you mentioned. So one thing, as you've also mentioned, the difference between laser versus flash lamp, and also, let's say, versus other types of methods of heating. Can you, for my education at least, tell me the pros and cons of
Sure.
this method versus other, let's say, other mainstream methods as well?
Okay. So there are essentially four methods, right? One is infrared heating, and that doesn't really work for thermoplastics because it cannot attain that kind of irradiance levels.
Right.
Second, probably the first approach used for thermoplastics is hot gas torch, where you basically apply a flame onto the material itself. So it is very good for melting the polymer because the heat is directly absorbed by the polymer through conduction and convection, right? It's not a radiation problem, but it is extremely difficult to control. Yeah, in the sense that torch itself is quite difficult, and so that's why people move to laser. Laser has the benefit of very high intensity, very short wavelengths, but the cons are that you require an enclosure, right? It is not really portable in that sense. So you require very good laser protection.
Safety part of that.
Safety part of it. The other con, I would say, and that's what I'm realizing from this, is most of the laser, even though they are, you can have it in a grid, it is a single wavelength laser. So the absorption is dependent on how good your fibers can absorb that wavelength, right?
None of the methods, none of the existing equipment, you can control the wavelengths of the laser?
Not the wavelengths, the intensity you can.
Okay. Okay.
So typically laser wavelengths are fixed, right? So
okay.
intensity you can. And then you have the the problem of refraction and specular radiation and so on. The arc flash lamp, on the other hand, is broadband radiation, right? And then so it has more opportunity for the heating of the fiber itself. But again, you have quite a bit of parameters to choose from for controlling, and you also need the cords to be very close to the tape to really project that intensity, because you have seen from the charts it decays quite quickly as you move away from the source. But the pros are, you don't need enclosure. So that was one of the reasons I went for it, because we want to be able to, Air Force wanted to be able to use this as a portable system, to be able to take it wherever they want, right? Closer to the forward operating bases. So that's the investigation we are doing.
And then what about in terms of surface geometry? Is there any limitations on this method versus, because you said you have to get too close to the surface, or it doesn't matter?
So for the arc flash lamp, surface limitations, well, so the radiation and how it impacts the surface makes all the difference, right? So if the surfaces are too curved, then you have to change the positioning of the lamp itself to make that happen, make it work. But that is true for laser as well, and that is true for hot gas torch as well. So depending on the contour, you need to reposition, and I think there are very few folks out there who are doing that, right? Or you try to make a broad incident, broad incident. So people have done array of lasers instead of a single laser. So those are the techniques. But again, it's a complicated process. That's why digital twin is the answer, in my opinion. Yeah,
that's true. So I have more questions, but I don't want to dominate this Q&A. Questions from the audience, or should I ask my next question? I think people are shy, and I'm also a bit dominating the times typically. So I'll ask my other question as well. So you mentioned like the heating is one part of it, the cooling is the other part of it, and depending on how the convection happens, how fast you move, many other parameters, the cooling is being affected. So is it even possible to control the cooling in general, or no?
That's a good question. So typically, if you want to get good degree of salinity, you want to cool the system or cool the tape very slowly, right? So if you want to control the cooling, one way is you control the environment it is in. I think what you have at UW is a closed environment, closed heated environment system. So that is one way to cool, and also ensure that the cooling rates are very slow, right? The other is you can try to control the cooling through the mold itself, right? You have a heated mold, and you have to do heat transfer studies to see that. But if you're looking at a system which has to be very general and can do large panels or large structures, cooling is dominated what happens very, very close to the tip itself as it's moving, right? Controlling that, people have tried, or at least we are trying, is post laydown heating to delay the cooling rate. Then pre-laydown heating to improve the heating of the tape as it's coming to the toe. But again, it's right now, how do I put it? It's a more of an art than science.
Yeah.
And I know Marco will agree that to make any panel, in fact, it takes more time to set up the AFP system and run it. And it is notoriously difficult to make small parts with AFP. Not because it cannot, maneuver. It is difficult because getting the heat transfer right is extremely complicated.
Yeah.
So it's an open question. I don't know if there's a
way. I mean, honestly, it's also maybe highlight the fact that you still need to rely on a secondary heating step, you have to go through the autoclave to make sure all the uncertainty is taken care of.
That's true. Right now, we are
Right
hoping
now,
that, and that's because we don't know the thermal behavior, right?
Yeah.
If there was a way to predict it and then design our systems to be able to change the things on the fly, right?
Yes.
Or tailor it such that, you know, you don't need the secondary operation. You can. So let me put it this way. Right now, secondary operations are required because you might get good crystallinity on the top of the tape, but within the tape, you don't get that level of crystallinity.
Mm.
Yeah, because the heat transfer doesn't have enough time to pass through the tape itself.
Also, maybe from what you showed, maybe even edges of the where you're heating up, because there's less heat at the edges versus the center.
Yeah. So it's a whole lot of things that needs to be taken care of. And that is why we need secondary operations right now, just to, you know, raise the heat and cool it down slowly so that we can get good crystallization.
Right.
So the question,
even in terms of like, even if we could simulate it properly, I think you mentioned as well the boundary conditions. So there's some uncertainty in the boundary conditions now, and you try to capture it as much as possible. But then maybe the question is like, how certain can we be eventually? Do we always have to do this uncertain
Yes.
simulation, a stochastic simulation in a way?
Yeah, it will always be a stochastic simulation. And, you know, so that's why I see the role of machine learning, because if you were to run numerical simulations using a stochastic approach to run the numerical simulation, it's just untenable. So you need to reduce the models, we use machine learning.
Speed up. So in terms of boundary condition, you mentioned, and I didn't appreciate it, I think, before, and then when you were talking, it kind of occurred to me, the radiation itself and the emissivity of the surface, depending on the angle of the radiation, the lighting condition in the room, reflective, so some materials have more reflective surface, some materials have less reflective surface. How much humidity and whatever you have in the room affects radiation. So these are all affecting the boundary condition at the end, right? So these are all
That's true. But in the heating side, it is largely insensitive to these small changes in boundary conditions.
Okay.
Because the heating itself is very high intensity. So unless you have, you know, polished surface and very high humidity, extremely high humidity, you don't get that kind of variation.
Mm-hmm.
But definitely the cooling is what decides everything for you, right?
Yeah.
So you need to bring it to temperature, but it's cooling rate, which essentially decides your structural behavior.
Yeah. And also for the cooling rates, again, the convection around your part, let's say you move your robot moves fast versus slow, so the airflow would change.
Your edge convectivity transfer will change.
And that becomes a nightmare again to capture. Yeah. Yeah, it's a difficult problem, and we appreciate you tackling it.
No, I mean, as a community, I think it's a very interesting problem. There are very fundamental basic issues or sciences we need to tackle. Or we can just say in-situ curing is not possible.
That's what we do now.
So, but then we are giving up. So I think one way to approach this is that there's a lot to learn. And the more we go away from empirical based techniques to characterize our machine, and more towards these kind of digital twin, then we become machine agnostic, we become part agnostic, and we should be able to cover more. Can we get pure very high crystallization of say 30-40% within a part? I think we need a lot more research to get to that level.
Yeah. Thank you again. And I have more questions, but again, we are running out of time, and I don't want to. Marco, do you have any?
Yeah, I was going to ask one quick question. I was listening to the discussion because I think, Navid, you asked all the questions that I wanted to ask as well. And first of all, Paul, outstanding presentation. I really enjoyed it. I
Thank
think
you.
this is what we need in the community, right? I mean, I've seen other presentations where people talk about some aspects of the problem, but this is the first time that I see a nice comprehensive presentation that goes over all the aspects of heat transfer for this problem. So you mentioned that the next step, one of the next steps, right? One of your future endeavors is going to be to model the process of crystallization, right? You mentioned a multi-scale model. I think it was one of the last slides. So do you have any insights on what is the numerical approach that you're trying to use? There is some work in the literature, but it's very sparse, and
Yeah.
I haven't found a clear winner yet. So I'm curious to get your insights.
So very good question, Marco. And I'll tell you this. We have to be cognizant that most of the literature is based on uniform heating and uniform cooling using DSC or, in an oven or whatever. So directly using those kind of data is not suitable for what we are doing. So we really need ray tracing, like I showed, to be able to see how the irradiation on the tape as well as on the fibers. Then we need a very good technique to understand how the heating between the fibers and the matrix happen, and then how the cooling happens. So all of this need to be accounted for, and that is why you need a multi-scale simulation approach. There is, in my literature review so far, this is possibly, let me just go to that slide. This work by Stotty is possibly the nearest I've seen, but this is again a single one-way simulation. That means they just do ray tracing and they look at heat transfer. But there are complexity to that as the crystallization happens, the degree of irradiance coming on the tape changes and the rate of cooling changes, right? So it is a multi-scale, multi-physics problem. And so we are trying to do all that. We're trying to see how we can use ray tracing coupled with the crystallization as well as the heat transfer problem. And I must say, it's just thinking about it hurts my head. So it's quite complicated.
That makes two of us. I agree. I mean, it's a very complex problem, and it's very difficult computationally because there are many length scales involved.
Yes.
So even when you use a multi-scale approach, being able to run these multi-physics simulations, even on a small scale, becomes challenging. So yeah, I think you have work for the next 20 years. So that's great. That's what you want.
No, I mean, it is a very challenging and very interesting problem.
Yep.
And if you can do this to some extent, then there are other problems you can definitely solve, not just related to AFP, So yeah, I think it's a very exciting work.
Yeah, thanks for
Work
sharing
to
it
be
with
in.
us.
Yeah, absolutely.
Yeah, Paul, thanks a lot again. We are out of time. We appreciate again you coming here and sharing your wonderful research with us. Hopefully, we will see you in person at some point in Seattle.
Yeah, I'll be at AIAA if you guys are there. So
yeah.
certainly.
This year, I'm not gonna be there, but next year probably. So I think
Sure.
Yeah, the earliest would be SSTM that we're gonna see each other in person probably.
Yeah, and if you guys are coming down to Houston, come and make a trip up to Dallas.
Definitely.
And,
Thank you. Thanks again. Thank you everyone for attending this wonderful talk, and looking forward to having you for our next talks. Thank you very much. Have a good day.
Thanks, everyone. Thanks,
Bye.
Naveed.
Thank you. Bye.